ENME 351, Lab 4, King Ralph. The Arduino code for this lab used the micros function to create a timing loop. The frequency value would be selected from the analog input connected to the potentiometer, and then the frequency would be converted to microseconds. Then after that time passes, the code takes a sample of the wave from the end scope and prints it to the serial monitor. Here I show each reconstructed wave and their correlating amplitude spectrum plot. I labeled each wave with the frequency, the sampling frequency, as well as whether the wave was aliased or not. We noticed that in order to accurately reconstruct a signal, the sampling rate fs must be greater than twice the highest frequency of the signal, unless the signal will be aliased. Here is a screenshot of my end scope. After performing the calculations and using the folding diagram, I was able to find the alias frequency and complete the chart. Here is my chart, and we see that the data closely follows the Nyquist criterion. The Nyquist criterion states that by defining the Nyquist frequency Fn equals Fs over 2, any analog signal can be recreated if Fn is greater than Fn. This means if the maximum frequency is less than the Nyquist frequency, when we sampled the signal at this rate, we get a reconstructed wave. This is seen in the data because when the maximum frequency is less than the Nyquist frequency, there is less aliasing seen in the data. But when the Nyquist frequency is more, we notice more aliasing in the frequency. Aliasing happens because the low sample rate causes a false signal to be observed, which is indistinguishable from the higher frequency content. Take a look at my physical setup of the Arduino and the potentiometer connected to the end scope. Then we see the square wave and the triangle wave run in real time. In the reconstructed square and triangle wave, and with their amplitude spectrum plots, we observe the Fourier series phenomena. Fourier says that all periodic signals can be described as a constant term plus an infinite series of sines and cosines. These infinite terms or harmonics may have different amplitudes and resonate at different frequencies. These frequencies are all multiples of the natural frequency. In the square wave, we see many different harmonics needed to reconstruct this wave. The amplitude decreases as the frequency gets higher, and these harmonics contribute to a flat top of the wave. When we take a closer look, we see that the tops are still resonating. We also see the spacing between the frequencies are similar when they resonate at multiples of the natural frequency. In the triangle wave, we see the same thing except less harmonics to get an accurate reconstruction of the wave. The Fourier transform allows this analog signal to be reconstructed in a discrete manner.